You know that click, right? That little sound when an Ethernet cable snaps into place? It's so satisfying. And it's the sound of a solid, stable connection, something we totally take for granted. We use these things for everything, from our game consoles to the entire backbone of the internet. But have you ever stopped to think about what's actually going on inside? Well, we're going to dive in, because this humble-looking cable is, well, it's a work of genius.
So how does it do it? I mean, how does this cable stay so unbelievably reliable? You can have a whole mess of them tangled together running past all sorts of noisy electronics, and it just works. How does it pump all that data through almost perfectly? The answer isn't in that plastic plug. No. The real magic, the big secret that makes it all possible, it's all in the twist.
All right, so to really get why that twist is so important, you have to know what it's fighting against. Think of it like a battle, and the enemy, it's electrical noise, it's interference. See, when you're shooting tiny data signals down these super thin copper wires at incredible speeds, they are really, really vulnerable to getting messed up.
And the main villain in this story is something called crosstalk. Picture this. You've got 8 little wires all running side by side, super close together inside that cable jocket. When a signal zips down one of those wires, it creates this little magnetic field around it. The problem is that field can actually leak over and create a little ghost signal in the wires right next to it. It's like the wires are whispering to each other and messing up the main conversation. And this is a huge deal. In the world of networking, that unwanted whisper, that noise, it just wrecks the data. It causes errors, which means the data has to be sent again and again, and that just grinds everything to a halt. It is the #1 thing stopping us from getting those lightning-fast speeds we all want. So, how do you beat it?
You fight it with an idea that is so simple, it's absolutely brilliant. You twist the wires. Instead of letting them lie flat next to each other, you take the 2 wires that make up one circuit and you just twist them together. Now, this isn't to make it look neat and tidy. Oh no, this is pure, clever physics at work.
Okay, get this. This is how it works. Because the wires are twisted, any noise that comes in from the outside hits each wire in the pair at a slightly different time. So one wire gets zapped with the up part of the noise wave and the other gets hit with the down part. Then, at the other end, the receiving device looks at both wires and basically says, hey, this weird signal is positive on one and negative on the other. It must be noise. And it just cancels it out. Gone. And it gets even smarter. Each of the 4 pairs of wires has a slightly different number of twists per inch. Why? So they don't create crosstalk with each other. How cool is that? It is just so elegant. So, problem solved, right? The twist gives us a clean signal. But that's only half the battle. Think about it. How do you make sure that a cable made in one factory works with a laptop made in another, all across the globe? You need a universal language. You need a standard for how to arrange those 8 little colored wires in the plug. And that's where these 2 names come in, T568A and T568B. These are the 2 big global standards. They're basically just recipes that tell you exactly which color wire goes into which of the 8 little slots in the connector. And honestly, the only real difference between A and B is that the green pair and the orange pair swap places. That's it. Electrically, they do the exact same thing. So, of course, the question everyone immediately asks is, which one's better, right? If they're pretty much the same, does it even matter which one I pick? Is there a right answer here? And the answer is, not really. You'll see T568B way more often in businesses and data centers. T568 pops up sometimes in homes or government projects. But here's the one rule you cannot break. Be consistent. Whatever standard you use on one end of the cable, you have to use the exact same one on the other end. That's the only thing that really matters. Just pick one and stick to it. Okay, let's talk about the plug itself for a minute. That little clear plastic thing we all know. You might hear it called an 8P8C, but we all just call it an RJ45. And it's great, for an office. But what happens when you leave the nice, clean, carpeted world behind? Because the real world is a lot tougher. I mean, what if you need that same solid connection on a factory floor? We're talking dust, maybe some moisture, and just constant shaking from heavy machines running all day. That little plastic clip on your standard cable, it's gonna snap or just vibrate loose. The connection is gonna drop, for sure. So for those jobs, you need a tougher solution. Enter the M12 connector. This thing is an absolute tank. It's metal, it screws on, so it locks down tight. It creates this perfect seal that keeps out dust, water, you name it. It just laughs at vibrations. It's basically the heavy-duty industrial big brother to the office RJ45. And this quote really says it all, doesn't it?
The connector that basically runs our entire digital world was originally designed for one simple job: plugging in a telephone. I mean, that's it. It's amazing it has worked this well for so long, but it also shows you exactly why, when things get serious, you need something that was actually built for the tough stuff, like that M12. Okay, so we've got a cable that can send clean data anywhere, from an office to a factory. Awesome. But you know, engineers, they are never satisfied. They looked at this cable and thought, we're already running one cable to this device. What if we could get rid of the power cable too? What if we could send electricity down this exact same line? And that thought led to Power over Ethernet, or what everyone just calls PoE. The name says it all. It's a technology that lets you send electrical power through the very same wires that are already carrying your internet data. This is a game changer because it means you don't need to find a power outlet for things like security cameras, office phones, or those wireless access points on the ceiling. Now, this sounds simple, but trust me, the engineering behind it is wildly complex. I mean, look at the schematic. You can't just dump raw electricity onto the same wires as your delicate data signals. You'd fry everything instantly. PoE is this incredibly smart system with special electronics on both ends that can cleverly separate the power from the data. It makes sure the volts go to the power circuits and the bits go to the network chip, all without them ever messing with each other. And this is why it's so useful in the real world. PoE is the reason so many installations can be so clean and simple. You see a security camera mounted high on a wall with just one wire going to it? That's PoE. The phone on your desk that doesn't have a separate power brick? That's PoE. It's all thanks to this brilliant bit of engineering hidden away inside. Wow, okay. So we've gone from the deep physics of why we twist wires to the color-coded standards that let the world connect, all the way from a cozy office to a noisy factory. Let's wrap this up and put it all together. Because now, if you were to actually make one of these cables yourself, every single step would make so much more sense. You strip back that outer plastic, you carefully untwist those pairs, but only just enough because you know you need that twist to fight noise. You line up the colors in that T568B or A pattern, get them perfectly flat, and crimp it. Every one of those actions is tied directly to the brilliant engineering we've been talking about. So, next time you plug in one of these cables and hear that little click, maybe you'll think about it a little differently. It's not just a piece of plastic in copper. It's an entire system. A system that starts with a simple, clever twist, uses a global standard to talk to everything, gets tough when it needs to, and has even evolved to do two jobs at once, carrying data and power. It really is one of the quiet marvels of our modern world. And that just leaves one last question, doesn't it? This humble cable has evolved so much already, from carrying a few megabits of data to tens of gigabits, and from just data to data plus power. So you have to wonder, what comes next? What's the next seemingly impossible job we're going to ask this little twisted pair cable to do?